this chapter, which is pretty much the last chapter we're going to cover, talking about another type of moment. It's called the moment of inertia. Okay, if you look at this title, moment of inertia, actually you may think about, oh, this is the fourth type of moment, which is a continuation based on chapter 3. Well, the answer is no. Okay, so this in reality, the called moment of inertia actually is not the real moment. In other words, this moment, if you look at it, if you later on check out the unit, it's not Newton times meter or pounds times inch. It's not. It's a totally different one. I have no idea why it's called. Probably 100 years ago, people at that time didn't carefully think about what that moment mean. Okay, so that's why they just happen to give a name, and now we just have to follow those people's original ideas. Okay, but it is somehow a little bit related. Last chapter, because now I can talk about more about the so-called moment, because we just finished chapter 7. Chapter 7 talks about beams. Beams is basically the most important structure for structural engineering and aerospace engineering, I believe. Okay, when you are ever studying the structural response or mechanical response of a given structure, because the beam is the most important, most widely used. Okay, when we talk about beams from last chapter, we already know how to plot the shear and the bending moment diagram, but that's only part of the story. Okay, you also need to know how to calculate the deflection of the beam, which I did not talk about now because that needs advanced knowledge. So pretty much you start to learn how to calculate the deformation of the beam when you take 150, whether CE 150 or MAE 150, when you are entering junior year. That means last fall. Most likely that's your first time to take 150. That is going to talk about the deflection of the beam. The calculation of deflection of beams is also very important, because when we design beams, not only we need to look at those shear and moment diagram, we also need to look at the deflection. Because when you see a bridge deform quite a bit, and nobody wants to drive on it, right? Because that can be somehow dangerous. But so far, from what we learned in chapter 7, we never talk about the deflection. In other words, we don't know how to calculate deflection. The bottom line is, in order to calculate deflection, you need to know this concept, which is called the moment of inertia, because this is basically telling you how rigid of the beam is. Okay? So how rigid of the beam? You may say, well, that depends on the material. If I gave you a wooden material compared with a steel material, that obviously the two beams are different in terms of the rigidity. The answer is yes, but that's not enough. Okay? Sometimes you can use a relative soft material to build a much stronger beam if you can design the geometry very well. So in other words, the final rigidity of the beam is dependent on the material, number one, but also dependent on the geometry of the beam cross-section. And that part, in fact, is called the moment of inertia. So the beam rigidity, in other words, called the flexural rigidity, is basically E times I, EI. E is the Young's modulus, or the material stiffness. That's called E. And then I is called the moment of inertia. We're still using I in this chapter. So this chapter basically talks about the moment of inertia, which is totally controlled by the cross-section geometry of a given beam. Okay? Well, first of all, the first slide just show you why we are concerned with this, what we call the moment of inertia. Okay? When you look at any beams, in fact, we just have to calculate, because later on when you need to calculate the deflection or anything, any beams, columns, we need to use that concept. Number two, sometimes when you are designing a dam to hold a reservoir, for example, we will see those pressures on this side is proportional to the depth of the water. For example, let me just give you this part of the story. So when we have the water all the way from bottom to the top waterfront, right? So you are concerned with the pressure on this side due to the water, okay? Because due to the self-weight, at any point inside there's a pressure given by the water. And this pressure, let's say the pressure is called delta F, which is the specific weight of the water multiply the depth from the top waterfront to here. That's called the depth. And then multiply with the tiny cross-section area. And then later on you need to do the integration in order to get the force due to the water at this point. So then you basically have the unit force, and then you add them together. That you can call resultant force or anything. And it's a summation of all forces. And this one is small, tiny area with this force plug in here. So you are going to have R summation delta F. And then summation later on become in integration because this continues. And delta is a P delta A. So then when you have an infinite part, that's delta A become dA. And what is a P? P is gamma, the specific weight, multiplied with the height, as I called Y. So this one plug into here, you have gamma Y delta A. So gamma Y delta A become dA, and then do integration. That's a resultant force. So then gamma is a constant because the specific density or weight of water is constant. That's 1.0 with some unit. I cannot remember exactly. So you put them outside because it's constant. And then you are dealing with integration YdA. So if you look at this YdA, and if you ever recall what you have learned, chapter 5, we should be pretty familiar with integration dA. And that's called Y bar, in fact, right? No, I'm sorry. That's the first moment. And the first moment divided by A, that's called Y bar. That's the Y component of centroid. Okay? And then at that time, we call this term, instead of having gamma, just this term, integration YdA, is called the first moment with respect to x-axis. And at that time, I told you, we would introduce another one which is called the second moment. Because this is the first moment, because that's with Y only. So Y is the linear term. That's called the first moment. But now, if we are saying there's another moment called the second moment, most likely going to be Y squared dA. So now we're telling the story about Y squared. Why we have Y squared? So Y squared is related with a moment due to those pressures acting on the dam. So for example, you already have the pressure everywhere. Now we want to calculate the moment of this pressure on this dam. So then not only you need to have this R, you need to further multiply with another Y, because each tiny force multiply with another Y to get the moment of that tiny force at that point. And that's called Fd, right? So you already have this F and multiply with a shorter distance. So this tiny force itself already has a Y. And then here you need to multiply another Y to get the tiny moment. And then you add them together. That's going to be the total moment, which is finally still have a gamma here, integration, originally have YdA, you need to multiply with another Y. So that's why I finally end up with Y squared. So in reality, when we are studying structural engineering problems, not only we need to study this term, which is related with the centroid, we also need to study this term, which is related with the moment calculation. And this one is called the second moment, or it is called the moment of inertia. Or the complete term now is called the area moment of inertia. It's trying to indicate this is not the real moment. It's not a force concept. Because in reality, if you go back to look at this term, right, this integral Y squared dA, if you want to study the unit of this one, Y in a way is a meter or inch. And then A is meter square, right? So Y is meter and Y squared, meter square, and then times a meter squared, that's going to meter to the fourth power. And that's the unit of this, what we call the moment of inertia. See, this unit is fundamentally different from the moment we talked about in chapter 3. Because in chapter 3, if we need to calculate the moment, the unit must be force times distance. In other words, it's going to be Newton times meter. That's a unit of that kind of moment we talk about. But now, this moment of inertia is basically a geometry concept. It's just basically the integration Y squared dA. And then how we're going to integrate out depending on what kind of area we're talking about. Okay, which I'm going to show you with some examples later on. Okay, anyway, the bottom line is the area moment of inertia, and we always just simply call it moment of inertia, in reality is not the moment we talk about in chapter 3. If you really want to see the tiny kind of connection, this one will be used. This part, later on we call I, will be used later to calculate the bendings, the beam's deflection due to the moment applied or due to distributed load applied. Okay, but so far you just need to, you don't have to make any connection between this moment of inertia with the moment we talked about before. Okay, now since this is important, then it's a question of how we're going to calculate that y squared dA integration. Again, we're no longer talking about this anymore because we already studied this very carefully in chapter 5. So now we just need to study this one, which is quite similar to what we talked about in chapter 5. So depending on what kind of specific area we're going to talk about, to analyze what we call the y squared dA. Okay? So y squared dA integration about the whole area you call A. It can be this area, or it can be this area, it can be any area. So we in general need to do the integration if we were given with a specific area. And when we talk about beams, if you look at the simplest beam, the cross-section area is typically a rectangular beam. So if it's a rectangular beam, then the question is how are we going to calculate the moment of inertia or the second moment, which is y squared dA. Okay, then obviously I'll show you this one through the overhead projector. But if you look at this one, finally end up with 1/3 BH cubed. In other words, this B, this is H, the height is H, and this width is B. You can see it's 1/3 BH cubed. So this indicates the moment of inertia is 100% dependent on the geometry only. That's why there's another reason why it has nothing to do with the bending moment we talked about before in chapter 7 or in chapter 3. So now I'm going to switch to the overhead projector, the document camera, to show you how we can integrate this out and finally end up with this one. And sometimes if you are using a different coordinate system, you can get a different result. Okay, so the first thing I'm going to do is to calculate the moment of inertia. By definition is a y squared dA with this A indicating a rectangular shape. Okay, before doing this, we need to set up the coordinate system. Okay, obviously there's many ways to set up the coordinate system. Let's say if we first set up the coordinate system like this, having x in this horizontal direction on the bottom side of the rectangular cross section, and then y is this, or in the middle, that's fine, it doesn't matter. Okay, so if set up this one, then obviously we can calculate I out. But later on I'm going to also show you if I want to change the coordinate system to this, and this is corresponding to the centroid located at the original point. So if we're talking about this one is x prime, this one is y prime, obviously this is a geometric center, right? For any rectangular shape area, then the centroid obviously is at the center of the original point, okay? Because that's a simple geometry, okay? So we do both. So going back to look at the first one, what we're going to do to integrate out is using the basic technique you learned from what's called the Math 2D, right? So Math 2D told us in order to do this kind of two-dimensional integration, you need to first split dA into dx dy first, okay? And that is a pure two-dimensional integration. And the typical way to do is to make a tiny strip in one direction. You can, for example, having this whole area dA which is the tiny strip here, so that from the bottom to here, typically called y, and then a little bit increment is called dy. Okay, so then this dA you chose gonna be b times dy. Okay, and this is the width of the horizontal distance, so that we're gonna plug in this one into here, or called dA again, like here. So it's gonna be y squared times b times dy. You may say, why not to form a tiny strip like this? There's really nothing wrong if you are using dA, which is equal to h times dx. There's really nothing wrong. But you won't be able to solve this problem because your integrand is y squared. If your integrand is x squared, in fact, that's exactly the way you have to do. But you have to look at your integrand, which is a function of y, so it's better split into this way, so that this one will become b y squared dy. So from two-dimensional integration all the way immediately down to one-dimensional integration. That's very easy. Okay? So what is the y squared dy integration? That's going to be 1/3 y cubed. Okay? And now we just need to identify the lower bound and upper bound with this given coordinate system. So if you look at this is x and this is the y, we're talking about dy. So the minimum y is from 0 all the way to the maximum y, which is h. So that's going to be 0 all the way to h. So the lower bound, upper bound. And then just plug in back to this one. You have 1/3 b times y cubed, 1 maximum equal to h, minus 0 cubed. So you finally end up with 1bh cubed. Okay? And that's exactly what I was showing you before. Okay? So this is the moment of inertia of this I, which is y squared dA. Any questions so far? Okay, original two-dimensional integration, but through this process we can easily integrate out using, in fact, one-dimensional integration. Now, as you said, as I just mentioned, how about this one? In fact, we are going to use this one. This time we can evaluate another one. Instead of having y squared dA, how about x squared dA? In fact, this is also called the moment of inertia. So either y squared dA or x squared dA, they are both moment of inertia with respect to different axes. So y squared dA integration, that is a moment of inertia with respect to x-axis, in fact. So that's why we typically use Ix to represent the moment of inertia with respect to axis x. And then x squared dA integration, that is called a moment of inertia with respect to y-axis. So when we talk about moment of inertia, we are talking about two kinds of moments of inertia. One is with respect to x-axis, that's called Ix, and one is called the moment of inertia with respect to y-axis, that's called Iy. Okay, so similarly, we can do this integration out by picking a tiny dA in vertical direction. So this one is also dA, but this time this dA will be h times dx. So then what we're going to do is x squared dA is h times dx. Now we can also do this integration out. H is constant, x squared dx, then is h over 3 x cubed, and then lower bound, upper bound. So if you look at this coordinate system, the minimum of x you can choose is 0, and the maximum you can choose is b. So that's going to be 0 to b. So then you can easily work it out, which is 1/3 hb cubed. So this is the moment of inertia with respect to y-axis if the cross-section area is rectangular. Okay? So now, I have a fundamental question by comparing these two results. Okay? When you are later on taking 150, That's the concept you must know to better design a beam. For example, let me just use this one. So let's say this is the beam. So you want to design the beam like this way, or you want to design the beam like this way. So just imagine, using your common sense, if I have a beam like this, when we gave the moment, okay, trying to bend this beam, compare with this kind of moment, this kind of beam, and trying to bend the beam. Which one you can easily bend, which one you cannot easily bend. So this is very difficult to bend, okay? Think about it. This is very difficult to bend. But this one, if you want to bend this, it's relatively easy. But now the question is why this is easier than this? When you're trying to, you gave the same amount of moment, you just want to bend this one. Why this is much easier than this one? The answer is just right here. If you are looking at 1/3 BHQ very carefully, the area is the same thing, right? So when you talk about this beam, this obviously very short, assuming this is very long, okay? This is very long, okay? So you cut it, the area is the same thing. This area versus this area, the same thing. But that I is different. Because look at this one, if this is a cross section, this is H, and this is a tiny b. So H is much larger than this b. And if you go back to look at this b times h cubed, you imagine a number, compare with this one when you have the same cross-section area. However, this becomes your new h, and this becomes your new b. So this h is very tiny, and b is much bigger. So now you're going to use the same equation, 1/3 BH cubed. You see, comparing the increase b versus the increase of h. b is a linear, and h cubed is a nonlinear. So that's why you would like to design some beam with the larger h, so that it's difficult to bend. The same material, right? The same cross-section area, the same span. So if you can design well in order to increase this I, then you can have a much stronger beam. And that's exactly the concept from the moment of inertia. So let me go back to look at the result I just showed you. Okay, so if you want to design a beam with a higher moment of inertia, you need to increase h instead of increasing b. Increasing b, obviously you're going to increase the moment of inertia. There's no doubt about it, but it's not very effective. If you want to increase this h, it's going to be very, very effective. Okay, so that's the first concept when you are using a rectangular beam. You would like to hold this beam like this way instead of having the beam like this way. If like this way, you have a smaller h. So this is the moment of inertia with respect to x. But then, of course, if you are changing the coordinate system, instead of choosing this as your coordinate system, if you are changing the coordinate system to this and this, then are you going to have the same moment of inertia? And the answer is no. The answer is no, but it's not that much. The reason it can be different is because of y squared dA, and y is heavily dependent on the coordinate system you chose. So now I'm switching back to the overhead projector just to recalculate the moment of inertia, which is called Iy, which is defined x first, y squared dA, but based on this new coordinate system we chose. Okay, when we see what kind of answer we can get. Okay, so we do the same thing, right? So we're gonna find out a tiny strip here. Okay, and that's called dA. So that dA will be again b times dy. So it's nothing changed. And b is constant, we put b outside, and still y squared dA, nothing different. And b times 1/3 y cubed, lower bound, upper bound. But now, because of a different coordinate system, the lower bound and upper bounds are changed. Nothing else is changed yet, right? Only the lower bound and upper bound changed. Now this time, this is the x and this is the y, then what's the minimum y? The lower bound. This is the lower bound. That's going to be negative half h. Okay? What is the upper bound? This is the upper bound, which is a positive half h. Okay, just because of the lower bound, upper bound change, then the result is different. The result is different. So let's plug in b over 3. Upper bound of y is half h cubed minus lower bound of y is negative h cubed. Okay, and you do the simple math. So finally, that's going to be h cubed over 8. So b over 3, h cubed over 8, and negative again become positive, h cubed over 8, right? So that's 1/4. Multiplied with 1/3, that's 1 over 12 bh cubed. Okay, so the result is a little bit different. It's still bh cubed, there's no doubt about it, but the coefficient in front of bh cubed is 1/12 instead of 1/3 at the very beginning if you change a different coordinate system. So from these two examples, clearly you can see the moment of inertia is somehow related with the coordinate system you chose. Okay? However, the fundamental terms having the geometry remain the same. That's bh cubed. So that's why when you are designing a beam, the most important thing you need to look at is the height. But the coefficient, that's a secondary issue. Similarly, for this new coordinate system, you want to calculate Iy, which is the definition of x squared dA. You do the same thing. So x squared dA this time, you can choose a tiny strip in this vertical direction. So that's going to be h times dx. And then you put the h out, x squared dx, h, that's 1/3 x cubed, and then lower bound, upper bound of x. So you're talking about this coordinate system, the lower bound would be negative half b, the positive half b. Okay, so then you plug into the equation x cubed, you finally end up with 1 over 12 b cubed h. This is the moment of inertia with respect to y-axis if you set up the coordinate system at a central location point. Okay, so let me switch back just to talk about this one again. So if you are using a different coordinate system, then you may get 1 over 12 bh cubed. And everything we did is only for rectangular cross-section area. Obviously, if you are talking about different coordinate, different area, then obviously you have to do something differently, okay? The bottom line is, this is the definition of the second moment, or called the moment of inertia. The definition is Ix, which is called the moment of inertia with respect to x-axis, is defined as y squared dA. And correspondingly, the second type of the moment of inertia, which is called the moment of inertia with respect to y-axis, that is defined as x squared dA. And the moment of inertia sometimes is also called the second moment. Just try to compare with the first moment as we introduced in chapter 5 when we were trying to calculate the centroids.